open. Here we go. All right. So, yeah, good morning, everybody, again on this rainy morning. It would have been a good morning to sleep in, so sorry you all had to wake up. Because it's nice and dark out. So, yeah, so we are in 2-2. And if we just kind of want a quick review of Monday. On Monday, 2-1, we talked about quadratic functions and all about graphing them and the standard form of quadratic equations and just all the different things that we can do with quadratic equations. And then we moved on to 2-2, where we expanded our scope to include polynomials, right? So polynomial is, a quadratic is a type of polynomial. The quadratic's highest power is to the second power, but we can have polynomials up to any degree. So we have this kind of standard format here up to the nth degree. I think most of the polynomials we'll be dealing with are up to like the 5th or 6th degree, but you could have a higher degree polynomial than that if you really wanted to. And we talked about how we kind of know what the graph looks like based off of the leading coefficient. So the leading coefficient is a fancy word to just basically say the coefficient with the highest order. So if the highest exponent that we have was to the 5th power or to the 6th power, that would be our leading coefficient. In a quadratic equation, it would be to the 2nd power. So the leading coefficient actually gives us a clue as to what our graph is going to look like. All right, and so that's what this chart was about. If your leading coefficient is odd, so if you have x to the 3rd, x to the 5th, x to the 7th power, you're going to have your graph is either going to fall then rise or rise then fall, depending if your leading coefficient, the leading number, is positive or negative. Okay, and then the same with when you have a x to the 2nd or x to the 4th or x to the 6th power. So when your n, this is your n up here, is even, then you're either going to both rise or both fall. And that also depends on the leading coefficient, if it's positive or negative. So that's kind of a quick review of where we were at. And then we kind of started this, and then I said, let's just stop and we'll pick back up on today. So now it's today, and we are going to talk about the zeros of a polynomial function. So the zeros of a polynomial function are basically when, you can see there's a little chart here. The zeros of a polynomial function are basically when your function equals 0. Okay, so it's when the function crosses the x-axis. So for example, if I slip over to Desmos, there we go. All right, so if I put up a quadratic, a simple polynomial, and I wanted to know what the zeros of my equation are, it would be these 2 points. So it's where the function, or y equals 0, it's the values of x that make our function 0. So that's what we're talking about with the zeros. It's not when x equals 0, what does our function evaluate at. That's important too, because that's where our vertex is, right? But our zeros are talking about where do we cross the x-axis. Okay, so in this particular case, this quadratic equation is to the power of 2, and we have 2 zeros. So that's, if you look at the power, this power is 2, right? The most zeros that we could have are 2. So we have the most that we can. You couldn't come up with 3 zeros for this function. You're only going to have 2, okay? But we could have cases where we have less than 2. So that's the most number of zeros that we could have. So for example, if I just have my simple quadratic, y equals x squared, I only have 1 0 in this case. And now we'll actually learn in a couple sections that this is the only real 0 that we have. But if you remember, we also have our not just our real numbers, right? We have our complex numbers, our non-real numbers. So we're going to talk about that in a few sections. But today we're just worried about the real roots. And then if I did, this is why I had to be careful whatever I graphed. So if I have my green quadratic equation, do I have any real zeros to this equation? For the green one? Nope. That's right. Aiden says no. I agree, Aiden. We don't have any real zeros to this equation. There can be some in the imaginary side of the equation. And in fact, there are some imaginary zeros, but we don't have to deal with those in this section. We'll just save those for another day. Save that fun for another day. Okay, so we are going to do some practice about finding the real zeros of the polynomial function. Let's switch over to the notes here. So I am going to start with, yeah, we did up to 20. So we talked about rising and falling. We did that one. All right, so let's do a couple examples here. If we have a polynomial function, says we need to find the real zeros of the polynomial function and then determine the multiplicity of each zero. Use a graphing utility to verify your result. So we'll talk about what the multiplicity of zero means. It actually sounds more complex than it actually is. Okay. So let's start with number 26. Okay. So what they actually want us to do is, let me grab this here off to the side. Does anyone know what they want us to do to find the real zeros? All right, so in order to find the real zeros, it's actually not too complex of a process because we want to find out, if you remember from our graph, we want to figure out where our y or our f of x equals 0. Right? So if you refer back to the graph, we want to figure out where our y or our f of x equals 0. That's what we're trying to determine. What values of x make our function equal to 0? Okay, so for example, in number 24, 24 should be pretty easy, okay? So we got 24, we've got f of x equals 49 minus x squared, which equals 0. So when we have a function, a polynomial function, this is a quadratic function, but it's still a polynomial function. In order to find our zeros, we are going to pull out all of our fun factoring skills that you spent lots and lots of time in Algebra 2 honing your awesome skills to factor quadratic and higher equations. Okay, so this particular 49 minus x squared should be a pretty easy one to factor, right? This is a difference of two squares. So we could factor this as 7 minus x times 7 plus x equals 0. So I didn't change the equation. All I did is factored it, right? Yes. So then we know, this is my fancy math thing, if we have something times something equals 0, each one of the two somethings has to equal 0, right? So 7 minus x has to be equal to 0, or 7 plus 7 plus, that's supposed to be a plus, plus x equals 0. I apologize, that's a plus sign. So that basically means x equals 7 or x equals -7. So these are my two zeros of the equation. Okay, so then if I want to verify, use a graphing utility to verify my result, sorry, I just had to sneeze. Whoa. All right, we get a really big quadratic equation, but if I look at my zeros, they are at -7 and 7. Okay. The other thing, you might hear me actually slip because sometimes people actually, not people, mathematicians call these roots of the equation. So if you hear me say roots, zeros, sometimes they're used interchangeably. Your book uses finding zeros, so I'm going to try to stick to that, but you may sometimes find the roots of the equation. Okay. All right, so then let's actually try number 26 so we can talk about kind of another concept along with this. So 26 is right here. F of x equals x squared plus 10x plus 25. So we want to find out what value of x makes our function equal to 0. Okay, bust out our factoring skills, right? So we've got x, we've got 25. 5 times 5 is 25, and 5 plus 5 is 10. So we've got x plus 5, x plus 5. Oh, so we have exactly, Aiden. Or another way we could write this is x plus 5 squared. All right? So what are our roots of this equation? For this particular equation, even though it's to the second power, it's squared, right? We could have up to 2 real roots. In this case, we only actually have 1 real root at x equals -5. Okay, so that's our only real 0. Now, this is where that weird determine the multiplicity of each 0 comes in. So if you go back over here, determine the multiplicity of each 0. So I wish I had this up from my notes, but I don't. So I'll just explain it. So basically, if you have, when you go and you factor, when you factor your polynomial. So here's where we factored up our polynomial, okay? When you factor your polynomial, if one or more of your terms ends up as x minus some number to the k power, where k is greater than 1, then you have a repeated 0 or a multiplicity of k. Okay? So this is called a repeated 0 or a multiplicity k. All right, so now let's translate this into English. Okay, basically, what we just found when we factored number 26 is that we have one of our terms in our factor is still squared, right? So one of our terms is repeated more than once. So in this particular case, we have a multiplicity of 2 because the 0 at -5 is repeated twice. So basically what that means for this equation is that this has you're going to have to multiplicity, multiplicity of 2. That's kind of hard to see. This has a multiplicity of 2. So the root is at x minus 5, and it has a multiplicity of 2 because it's to the second power. So that's really all you have to do to deal with the multiplicity. Okay, so when I graph it, how many times is it going to hit the x-axis? It's only going to hit it one time, right? But that root is valid twice. It's a repeated 0. It's repeated twice. Does that make sense? So if I go to graph it, x squared plus 10x plus 25. All right, so here is our root. And you can see we only have the one point at which it hits the x-axis, right? But this represents two different, it's a repeated 0. It represents two different zeros of our equation. Exciting, right? So let's try one more that's like this. Because these are so fun, right? It is raining like crazy outside my house right now. All right. Let's clear some of this off. There we go. Oops. All right, so let's actually try number 30. All right, so we have f of x equals x to the 4th. So let's do a higher order polynomial. Minus x cubed minus 20x squared. So let's do some factoring. Factoring is fun, right? So what I first notice is I really don't feel like factoring like a 4th degree polynomial. But what I noticed that's kind of nice is that all 3 of my terms have x squared in it, right? So let's pull out x squared first. Oh, sorry. We want to figure out where this equals 0. That's how we're going to find our zeros, right? I notice all 3 of my terms have an x squared in it. So I'm going to pull out my x squared, and I'm going to be left with x squared minus x minus 20. And that looks like a lot more fun to factor than x to the 4th power. Okay, so let's see, can we factor x squared minus x minus 20? Aiden's got it. You must be the factoring man. Well, almost, Aiden. Yep. Say, do you enjoy factoring, Aiden? No, you just have done so much of it. You're like a factor master. All right, so we have x squared times x minus 5 times the quantity of x plus 5. And so if we FOIL these back together, we will end up with this quadratic. So that checks out. If you remember FOIL, x squared minus 5x plus 4x. That gives us minus x. And then negative 5 times positive 4 gives us negative 20. So that works out. So then if we want to figure out the zeros, remember it's each term. So x squared equals 0, or x minus 5 equals 0, or x plus 4 equals 0, Now you can do a lot of these in your head. So x either has to equal 0, 5, or -4. Okay. Almost done. Do we have any 0 that has a multiplicity? So this one does not. This one does not. But this guy right here has a multiplicity of 2. Because we have one of our factors, right, is to the squared power. So let's say instead we have pulled out an x squared. Let's say we could have, like this was x to the 5th power, and we could have pulled out x cubed. If we had x cubed equals 0, then that would have been a multiplicity of 3. That kind of click? Cool. All right, so let's throw this up in the graph really fast. Just to check your knowledge here before we graph it, x to the 4th power, that is our leading coefficient. What is our graph going to look like? Are they both going to, well, I just said it. It's even, so they're either both going to rise or they're both going to fall. Just kind of guess in your head. Do you think they're both going to be rising or falling before we even graph it? Check yourself, right? X to the 4th minus x cubed minus 20x squared. Fun graph. Got to zoom out so we can see it. Oh man. Got to set my window a little differently so I can see it. So if you ever want to set your graph in Desmos, you can set your X and Y axis by going under your settings. You can also do this in your TI calculator if you go under Zoom. I think it's Zoom. You can go in there and set it. All right, so let me figure out my zeros. We have a 0 at -4. We have a 0 at 1, a 0 at 0, and a 0 at 5. And this 0 has a multiplicity of 2. The other thing I want to mention while we're in here, if I think Aiden, you did this the other day. You already knew how to do it. But Sarah, for finding zeros on your TI calculator, because it's a little different than mine, if you actually graph it on your TI calculator, okay, it's right here, and then you go to your trace. There you go. Yes, second calculate, and then press 2 to select the 0 option. So it will actually tell you what your zeros are of a function with your calculator. And you can also just trace it along and try to get really close to 0, but this will actually tell you what the exact zeros are, which is nice. Aiden is familiar, right? Awesome. And then obviously on Desmos, you just click where they're at. I think there is some 0 function, but if you can click it finds the zeros for you, even if it's a weird, not a perfect number. All right, so then our last few examples that we have, I think are actually easier than finding the zeros now that we kind of understand what they are. So let's do those few really quickly here. Okay, so now in 49 through 58, and I have a couple examples here. It says, find a polynomial function that has the given zeros. There are many correct answers. So the answer that I'm going for is kind of the simplest answer. So what basically they are telling you is that, like in number 50, if I can get my pen to work. We have a 0 at -7 and a 0 at 2. Okay, so at a minimum, my polynomial function will at least have to be a quadratic. It'll at least have to be to the second power, right? Because we have 2 zeros, and so I at least have to be to the second power. So I try to make this as simple as possible. And so I know that one of my terms has to yield a result of, I mean, this is really making it complex, but basically x plus some value a has to equal -7. So I know it's x plus a times x plus b equals 0. All right, so one of my terms has to yield a result of x plus whatever equals -7. So you guys can probably figure out, no, I just wrote that wrong, didn't I? I'm writing this wrong, I'm not explaining it well. Sorry, I was doing it in my head and I'm like, oh, well, this is easy. And I'm trying to explain it better. Well, ignore that for a second. Let's erase that off here. Basically, what term do I need to get? This is what I did in my head, and I was trying to make it more fancy than it was, but I didn't explain it the right way. So what does this term have to be in order for x to be equal to, that's what I did wrong. That's what I did wrong. I want x to be equal to -7. But my original equation would be, I'm just not explaining this very well. All right, I want this to be x plus 7 because I know that if I plug in x equals -7, that x -7 plus +7 equals 0. I was trying to make it fancy, but I think I'm just going to go with the simpler, how I would do it in my head. All right. I'm making that more complex than what it should be. So I know this term should be x plus 7 because if I plug in x equals -7, then the whole term equals 0. All right. I'll try to make this one less complex. So my second term here, right? I know that when I put in x equals 2, the whole factor needs to equal 0. So for the second term, instead of a plus b, I would put in x minus 2. Sorry, I'm making this more complex than it is. So basically, when I put x equals +2 and I have 2 minus 2, we get 0 for the second term. All right, I made that way more complex than it should be. So we could say that one possible polynomial function would be x plus 7 times x minus 2. And then if you wanted to use FOIL, you could say it's x squared plus 5x minus 14 if you wanted to turn it back into a quadratic. So then if I go to graph this, kind of pull it all together, I should have zeros at -7 and 2. No, not t. X plus 7 times x minus 2. And now we have a function that has zeros at -7 and 2. Okay, let's do another one since I messed up explaining that one. Let's try one that, let's see if we can do the next one. I bet you guys can do this without me. So number 52. We have zeros at 0, 2, and 5. So I already know off the bat that my polynomial function has to be at least to the third power because I have 3 roots. All right? So we're going to go with the simplest form that we can. So one possible solution is that we have our first root at 0, right? And so in order to get a root at 0, we just have to have our single x. So we need the result x equals 0. Sorry, I just said roots. I meant zeros. All right, we have another 0 at 2. All right, so when x equals 2, our factor is 0. So in order to get a 0 here, we need to do x minus 2. Right? Because if x equals 2 and we plug it in, 2 minus 2 gives us 0. And then our third root is when x equals 5. So in order to get a factor that's 0, we would do x minus 5. Because if we plug in x equals 5, 5 minus 5 will give us 0. Aiden's got it all factored out for us. X cubed minus 7x squared plus 10x. All right, so then if I go throw this into Desmos, we've got x times x minus 2, x minus 5. Pretty little graph, right? We have our zeros at 0, 2, and 5. And again, there's other ways that you could do this, but I'm going for the simplest, even though I'm making it more complex. All right, one last little example, kind of similar, except we are going to have a few multiplicities going on here. All right, so the last examples are 60 and 62. That's not what I'm going to do. Okay, so in 59 through 64, a polynomial function with the given zero, find a polynomial function with the given zeros, multiplicities, and degree. There are many correct answers. Okay, so let's take number 62 here, okay? We have a 0 at negative 5, a 0 at negative 5, and it has a multiplicity of 3. All right, so we know that when we're going to write our polynomial function, we have a 0 at negative 5. So if I plug in x equals negative 5, what do I have to do to x to make it equal to 0? So I would add 5, right? Because negative 5 plus positive 5 is 0. And that is my 0. Now it has a multiplicity of 3. So that just means that this 0 is repeated 3 times. Also means that this happens to be to the third power. Okay. And then our second, second detail about our polynomial function is that we have a 0 at 0 with a multiplicity of 2. So when we have a 0 at 0, that means that we're just dealing with x, right? Because if we plug in 0 to x, we get 0. And it has a multiplicity of 2. So that means that this 0 occurs 2 times. And then the last piece of information is that they give us this is a degree 5. So if you look at our exponents here, we have to the x plus 5 to the third power, x squared to the second power. So that gives us our degree 5. And we can spend some time factoring or putting that back to standard polynomial form if we'd like. So then if we go to graph this, we should have a 0 at -5 and a 0 at 0, right? That pretty graph. All right, so we have a 0 at -5 and a 0 at 0. Sound fun? Woohoo! All right, any questions about that? I think it's pretty straightforward once you start dealing with it. You guys feel like you can tackle it? Awesome. Okay, we are going to continue a little bit into 2-3 because 2-3 is it's not difficult, but there's a lot of kind of work that goes along with it. So we just spent section 2-2 finding the zeros of polynomial functions, right? And when they gave us these polynomial functions to factor, they were functions that we could factor pretty easily, right? Aiden, we could, sit there and we're like, oh, okay, I can pull this out. I can, use my factoring skills. I can do all that. So now we're going to kind of move on to some other techniques when you have a function that's maybe not as easy to factor, or we're going to basically use some different techniques in order to factor our thank you, Aiden. All right, so Aiden has factored out our last problem. I didn't even do that, Aiden. So now I'm going to copy what you said. This is how I always like to make sure that I did it right, Aiden. I like to take it and I like to throw it in my calculator. Uh-oh. Maybe I copied something wrong. Something went a little bit off. But I think I would say it looks like a negative. It looks like a negative somewhere because this part's right. Hold on. Not that negative. We still went above and beyond, Aiden, so I'm sure it's just a negative somewhere in there. Something, right? So that's how I always like to check it. All right, so basically what we're going to do in 2-3 is we're going to have lots of fun factoring and using some different techniques to factor. Okay, so in Algebra 2, some of you may have done this and some may have not, but basically we're going to first learn a technique to do polynomial long division. So did anybody do polynomial long division before? Yeah, it's not too bad. But we're going to kind of learn how to do polynomial. There's a bunch of words here. We'll talk about it later. We're going to learn how to do two techniques to divide one polynomial by another. We're going to use long division and we're going to use synthetic division, which is kind of weird at first, but then once you see it, it's kind of cool. And then once we learn those two techniques, then we'll talk about how to actually use them. All right, so we're going to use two techniques to basically divide one polynomial by another polynomial. All right, so there's a lot of words there. We'll go back to those once we kind of figure out what we're doing. So this is going to take you back to your old school long division days. So we're going to start here with just long division of two polynomials. All right, so Should make that a little bigger. And exercise 1 through 14, use long division to divide. So we have 5x squared minus 17x minus 12, and they want us to divide it by x minus 4. Okay, so what we're going to do is we're actually going to set up a long division problem. Probably haven't done that in a while, right? Maybe you have. I bust out long division every once in a while. But our long division problem is going to look just like a long division problem you would have with your regular numbers. But instead of regular numbers, we're going to put our polynomial inside. So we have 5x squared minus 17x minus 12, and we are dividing that by x minus 4. So thankfully, the process of doing polynomial long division is the same as doing the process of regular long division. You're going to start with the largest value first and see what you can divide in, just like the same way that you do regular division. And I haven't taught regular long division in a while, so I think there's an acronym that some people use, but once you see it, you'll be all right. All right, so what we want to do is we want to look at our first term here. We have x, and we want to see, okay, what do I multiply x by to get 5x squared? So in order to get rid of my first term of 5x squared, I need to multiply x by 5x. So do you see that 5x times x gives me 5x squared? And that way, when I do my subtraction in my long division, I get rid of my x squared term. Okay? You'll notice when I put this here, I put the 5x over top of my other single x term. So you kind of match up where you put it on your long division with the same order variable. So we put those just on top of each other, just kind of a note for organization. All right, so if I multiply 5x times x to give 5x squared, I also have to multiply 5x times negative 4. All right, so 5x times negative 4 is negative 20x. Okay, so now when I do my subtraction, I have 5x squared minus 5x squared. So there's nothing left with my x squared term. That's a 0 there. You don't usually put zeros there, but that's a 0, right? Then I have negative 17x squared minus negative 20x. So that's actually going to give me positive 3x as my remainder, right? And then I'm going to bring down my next term. So 3x minus 12. So now I go back to the, back to the top, and I need to figure out, what do I put in my constant term? What do I put right here? Well, I have a 3x down here, and I have an x over here. So if I multiply 3 times x, I will get 3x down here, right? 3 times x, and it needs to be a positive. 3 times x gives me 3x, and 3 times negative 4 gives me negative 12. And then when I go to subtract them, I get no remainder. So it divided perfectly. So if I have 5x squared minus 17x minus 12 divided by x minus 4, the result would be 5x plus 3. That would be my answer. Now, practically what that means is that if you have 5x squared minus 17x minus 12. You could factor that as x minus 4 times 5x plus 3. Because we basically divided out one of the terms. They give you one of the terms, and you're figuring out what the other term would be in order to factor our original quadratic. So it's kind of a little bit different, kind of weird, kind of cool, kind of mathy, all that good stuff, right? So let's do number 6 and number 10, and then we will send you guys on your way. So we're almost done here. So I think just seeing a couple of them helps, you know, helps you do them. Once you see it, how does this feel? Like, okay, I can do that. Or what in the world? Or no comment. Everyone's like, I'm going to wait and see how the homework goes. All right, so number 6, we have 2x cubed minus 3x squared minus 50x plus 75, and we're going to divide that by 2x minus 3. Okay, so we have 2x minus 3, and we have 2x cubed minus 3x squared minus 50x plus 75. All right, so let's do some long division. Who thought when you get all the way to pre-calculus, you go back to long division, right? Okay, so what you're going to do every time is you're going to look and see, okay, my leading term here, I have 2x and I have 2x cubed. So what do I want to multiply 2x by to get 2x cubed? I want to multiply it by x squared, right? X squared times 2x squared will give me 2x cubed. And that's going to get rid of my highest order term. So that's a good thing. All right, but then I can't forget about my other term. So I have x squared times negative 3. So I get negative 3x squared. Well, that works out nicely. When I go to subtract my terms, right, I have nothing left over. So now all I have to do is bring down my 50x. Okay. And because I only have 50x to deal with, I think I'm going to go ahead and bring down my 75 as well, since I have two terms that I'm dealing with, right? So now I need to look at my 2x, and I have negative 50x down here. So what do I need to multiply by to get a negative 50x? I need to multiply by negative 25, right? And I don't want to put negative 25 here because I don't have an x term. So I want to put negative 25 down here because that goes in my constant slot. So negative 25 times 2x gives me negative 50x. And then negative 25 times negative 3 gives me positive 75. And that's nice. They work out nice and easily, right? So I would say that the result is x squared minus 25, or you could say that 2x minus 3 times x squared minus 25 equals our original equation. Okay. We have time for one last one super quick. I just want to show you this one because it's a little bit different. You guys think you can do this? I think you can do it. Maybe you're all doing your homework right now. You're done with it, right? Okay. Oh, now I have a nice box. All right, so this one's a little bit different. We have 1 plus 3x squared plus x to the fourth divided by 3 minus 2x plus x squared. So, of course, the higher number you get, the little bit more tricky you get, right? So when we go to write this out, you actually want to write your terms from highest to lowest. So the first thing they did is that they wrote these in reverse order, right? So we actually want to write x to the fourth power as our first item, right? And then when we get to, we don't have an x to the third power, but you actually want to go ahead and put a placeholder in for each of the degrees lower that even though they're not in your equation, because when you're doing your division, you might actually end up with an x to the third power and need to be able to subtract from that. So you'll see in my original polynomial, I don't have an x to the third power, but I want to go ahead and put a placeholder in there. So plus x, 3x squared. And then again, I don't have a x term, so I'm going to put in 0x plus 1. So now we have a really, really long polynomial, right? And then we're dividing by x squared minus 2x plus 3. Okay, so now we want to look at our first term is x to the fourth, and we have an x squared. So that's pretty easy. We're going to multiply. The first thing we're going to multiply is by x squared. So when I write that in, that's going to go over my x squared term down here, right? So I need to multiply each way. Okay, so x squared times x squared is x to the fourth. Okay, x squared times negative 2x is negative 2x cubed. So that's why I had to put my 0 placeholder in, because even though I don't have it in my original polynomial, I might end up with it when I multiply, right? And then my last term is plus 3x squared. So now when I go to subtract, x to the fourth minus x to the fourth, nothing, right? 0x cubed minus a negative 2x cubed leaves me with 2x cubed, okay? And 3x squared minus 3x squared leaves me with 0x squared. You can leave a 0x squared in there if you'd like. And then we want to bring down our 0x. All right, so now what do I want to multiply by to get my first term to be 2x cubed? And I have an x squared. I want to multiply by 2x, right? Because 2x times x squared gives me 2x cubed. All right, and then I want to multiply each of my other terms. So 2x times negative 2x gives me negative 4x squared. And 2x times positive 3 gives me positive 6x. So you can see where those zeros come into play, right? When I subtract it out, I end up with 4x squared minus 6x plus 1. All right. So how do I get a 4x squared term? I add 4 here. So 4 times x squared is 4x squared. 4 times negative 2x is negative 8x, and 4 times 3 is 12. So then I'm running out of room. When I go to subtract, I end up with 2x minus 11. Okay, so this actual, and I didn't even think this last one had this, but this actually has a remainder. All right, so when we divide our two polynomials together, our result is x squared plus 2x plus 4 with a remainder of 2x minus 11. And I'll talk to you guys on Monday about how we actually write the remainder. I didn't think this one had a remainder in it, but we'll talk about how you actually write the remainder on Monday. Yep, exactly. Aiden's got it. You put that over the divider. All right, so that is that. We are right at 10 o'clock. Sorry for keeping you guys the whole time. We just had so many exciting things to do, right? So that's long division, and then we're going to learn a technique called synthetic division on Monday that is another way of basically dividing one polynomial by the other. So thank you guys for sticking with me today. I know it was kind of a long day. We had a lot of stuff to do, a lot of math, but I appreciate you guys getting through it. So I hope you have a great rest of your day, and I'll talk to you guys on Monday unless I hear from you about any questions on the test. Yeah. Yeah, you should be able to do basically through 13. You might end up with some remainders. Yeah, you should be able to do through 13. Uh-huh. All right, guys. See you later.